Hello everyone, I hope you're good. We have a new lesson today, and our main idea of the lesson is how to draw the graph of a cubic polynomial or a cubic function. Alright. We know a cubic polynomial can be written in this fashion. This is the standard form of a polynomial, of a cubic polynomial. Alright, so how do we draw a graph that is a cubic? Previously, we have learned about a quadratic equation, a quadratic graph or a quadratic function. We know that a quadratic function will be of this nature, or it will take a curve of this nature or a curve of this nature. Now, this one, the cubic polynomial, is a bit different from the parabola or the quadratic equation. This one has two curved parts, simply a maximum and a minimum, while also touching our x-axis. We know if a graph here touches the x-axis, and at the x-axis y is equal to 0 over here, y is equal to 0 over here. So if y is 0 there and there's an existing x-intercept, there's an existing x value there, that is our roots. Our roots are simply just our x-intercepts. We're going to have three roots on this quadratic function or polynomial, compared to this one whereby we have only just two of these roots or x-intercepts. Okay, now that we have tried and explained how does a quadratic function look, now let us go into the specifics of how do you go about finding the relevant information that's necessary for you to be able to plot this graph of a cubic polynomial. All right. Firstly, we need to use something called a factor and remainder theorem. A factor and remainder theorem. Now, this theorem states that if f of k is equal to 0, then x minus k is a factor. What does this statement tell us? You see, this is the value of x here, and this is the value of k. X minus k, sorry, not the value per se, but x minus k. This x minus k, it should be something of this nature, like when we are factorizing a quadratic equation. You remember, we always come to find that our roots are in this fashion, whereby we have x minus 2 and x plus 1 for a particular quadratic equation. If we factorize it, this is still the same thing. So this thing says that if f of k is equal to 0, if this value over here is inserted here, 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 and it gives us an answer of 0 for a particular quadratic polynomial, then that value that we inserted there is our factor. All right. While having that in mind, let us take an existing cubic function graph and illustrate what I'm talking about. Okay, let us say we have this cubic function, f of x equals to x cubed minus x squared minus 5x minus 3. Now, the factor theorem says if I put f of x, I mean f of 2, or x being 2, and then I say 2 cubed minus 2 squared minus 5 multiplied by 2 minus 3. This gives me 8 minus 4 minus 10 minus 3. Okay. Negative 17 is going to be 18 minus 17. I mean 8, not 18. This is going to give me a negative 9. So it means that x is not a factor of this quadratic polynomial. Let me try a new number now. Let me try a new number. Remember, I want a number that will give me 0 as my final answer when I put it on my cubic function. Let me try 1. Let me try 1. Okay, it's 1 minus 5 minus 3. Okay, this cancels. It's minus 8. This one also gives me minus 8. And it's not giving me 0. Then it must not be the 1. Let me try another number. The goal is for this number to give me a 0 answer. Then I will know that that number is a factor of this cubic function. Minus, okay. this is going to be minus 1 minus 1 again plus 5 minus 3. So this is going to be a minus 2. So this is going to be a minus 2 plus 5 minus 3. So this is equating to a 0. It's equating to a 0. Then this is my factor. Therefore, x plus 1 is a factor. Is a factor of my cubic function, meaning that it is one of the 3 roots that I was talking about. Remember, I said a cubic graph has 3 roots. A quadratic graph has 2 roots. This one has a cubic, a quadratic. Well, it has two roots, and then this one has 3 roots. So this x plus 1 must be one of the roots that is there on my quadratic, on my cubic function or my cubic polynomial. Because it is a factor, it gives me 0. So basically, I'm really trying to find the x-intercepts. Those x-intercepts, we call them factors when we are talking about the factor and a remainder theorem. We call them factors because they give us the answer of 0. This answer of 0 is the y-intercept of the x. So it's a root. I don't know if I'm over-explaining it, but it is almost as similar to this thing. Okay. Now that we have found our factor all right, let us erase this. Now that we have found our factor, we have found that x plus 1 is a factor. Remember, we need to have 3 factors. We need to have 3 factors. This one is x. So for me to achieve the x cube, I must have an x squared here, no matter how, no matter what. For me to achieve the negative 3 there, those 2 things must multiply to give me a negative 3, right? So I must have a negative 3 here, because if I multiply these 2 numbers, they give me the negative 3. The only thing I'm missing here is the inner parts of my quadratic equation here. All right. How do I find this inner part now of my quadratic equation? How do I find it? Remember, this inner part here, when multiplied by something, it should give me the negative x squared. To find this negative x squared now, to find the value, not negative x squared, it must give me the value of the coefficient of x squared as minus 1. So this is our first method of doing this thing. We're going to multiply this 2 and multiply these 2. Basically, we're going to have x squared into bx. Why am I saying x squared? X into bx plus 1 into x squared being equal to the negative x squared there. For me to get the value of b, I must solve this. I'm going to get b. I'm going to get bx squared plus x squared equals to minus x squared. Then I take the x squared the other side. Bx squared equals to minus 2x squared. Then I divide the x squared with the x squared. I get my b being equal to negative 2. Oh, okay. Then I found my value of b to be negative 2. So it's negative 2x minus 3. Oh, all right. We have found our 3 roots now. The only thing that is left is for me to factorize the quadratic into 2 roots. Then we have all 3 roots. Then we have all 3 roots. Okay, let me further do this. X plus 1 into 2 equals to 0. So remember, I said to you, this here tells us that the 2 signs down here will not be the same. If it was a positive, it would have meant these 2 here will be the same. Since it's a negative, it simply means these 2 down here will not be the same. While they are not the same, the bigger number amongst the 2 numbers will take the negative sign. What am I saying? Which number, when I multiply here, will give me? Which 2 numbers, when I multiply, will give me a negative 3? It's a 1 and a 3, obviously. But then if I subtract these numbers, they should give me a negative 2. It is still a 1 and a 3. But remember, I told you that the bigger number will take the negative sign, meaning that the 3 will take the negative sign. Hence, the 1 will take the positive sign. So it's minus 3 plus 1. I've just factorized without using the quadratic formula, because I simply find it as wasting time. But somewhere it's necessary to use it. It might be quicker to use it instead of this, because sometimes the numbers might be too big or might be too small, I don't know. But if you feel you need to use the quadratic equation, you don't feel confident enough doing this, it's okay, use the quadratic equation instead to find those values of x. Okay, now we've found now our roots to be x equal to minus 1, or x equals to 3, or x equals to minus 1. Oh, okay. So we've got a graph that is sharing two values of x here. Alright, now that we have found our roots, this is the first way of finding the roots of our cubic function or our cubic polynomial. That's the first option you have. There's 3. This is the first one, and then there's the one for using long division, and then there's another one for using synthetic division. All right. Now, the next thing we need for us to be able to plot this graph, the next thing we need is the minimum and the maximum points of our graph. Remember, we have the x-intercepts now. We need the minimum point and the maximum point of our graph. How do we find the minimum and the maximum of our point? All right. Remember that at our minimum point of our graph, the graph here is, okay, let me draw a bigger illustration. We are going to refer to the rate of change for this, the derivative. From here up to here, on this portion of my graph, from here up to here, my portion of the graph is decreasing, meaning that the gradient here is negative. It's decreasing. And then over here, it suddenly stops. It doesn't increase nor decrease. So if it does that at this point, it means that our rate of change there is going to be 0. So if our rate of change does, if our gradient doesn't change there, it means f prime x will become 0 at that point. After this point, then it starts again to increase. And it does the same thing this side. It starts by decreasing, it starts by increasing. Then all of a sudden, it stops increasing. Then after that point, it starts decreasing. All right. So for us to get the x values of our local minimum and our local maximum, it means we must equate the derivative, or equate the f prime of x by 0, and then solve for x. That will give us the two x values of our maximum and minimum points. So let us derive the original equation. The original equation was x cubed. Yo, I'm running out of things. Was x cubed minus x squared minus 5x minus 3. We want, this is f of x. We want f prime x. We're going to take the negative, we're going to take the cube and multiply it with the coefficient of x. It's going to be 3x squared. We're going to take the squared, multiply it with the coefficient of x, minus 2x minus the 1 from the exponent there. It's going to be x. And then going to take the exponent there, which is 1, and multiply it with the coefficient of x. It's going to be minus 5. And then we're going to minus the 1 from the exponent, and it becomes exponent 0. Anything exponent 0 is 1. So 5 times 1 is 5. I mean, minus 5, negative 5 times 1 is negative 5. And then the constant over here, we just simply ignore it. We change it to be 0. So this is our derivative of the cubic function. So the derivative of the cubic function being equated to 0. Remember, I said the gradient over here is 0. So this represents our gradient. Where do we find the gradient being 0? Where do we find the gradient being 0? Okay, let me try and squeeze it in. All right, 3x x. The signs will not be the same, but the bigger number will take the negative sign. Okay. So which two numbers can I multiply for them to give me a 5? It's 1 and 5. Between these two numbers, the bigger number will take the negative sign, meaning the 5 will take the negative sign. But if I multiply these two numbers from here to here, and then multiply these two numbers again, the difference of these two numbers should give me a negative 2. How so? Okay, let's say negative 5 plus 1. This time this is going to give me 3x. This time that's going to give me minus 5x. What is the difference of these two numbers? It's minus 2x. Therefore, it goes back to this. So this is correct. You know what this tells me? It tells me that my first point, or my first x point for the two, which is the local minimum and the local maximum point, will be the first one would be x equals to 5 all over 3. And the other one would be x equals to minus 1. These are my x parts of the coordinate. X, remember I said x part. I haven't gotten the whole coordinate. Remember, a coordinate is made by x is to y. So I haven't calculated this one. I just got these ones. So let us go and take these x values and plug them into our original quadratic. If we plug this, we want to find what are the values of y when x is 5 all over 3 and when x is minus 1. Then we'll get the whole coordinates, both the local minimum and the local maximum. Okay, let us remove all of this. Okay, let's put this. Okay, this is minus 1. This is minus 1 also. This is plus 5 minus 3. This still gives me what? 0. So my first point, my first coordinate is going to be minus 1 is to 0. Minus 1 is to 0. That's my first coordinate. I haven't seen whether this is a maximum or the minimum part of my graph. I'm going to see that when I plot these points. But I can also see if I have gotten the other one, then I'll be able to spot, oh, this one is lower than this one is higher than this one. Then I'll know this is my local minimum, this is my local maximum. So let us now put in the 5 all over 2, the 5 all over 2, the 5 all over 2. Let's put in the 5 all over 2 now. See what we get. 5 all over, sorry, not over 2, all over 3. 5 all over 3. 5 all over 3. 5 all over 3. Okay, so let me just simply use a calculator for time purposes to get this. 5 all over 3 5 all over 3 all cubed minus 5 all over 3 all squared minus 5 into 5 all over 3 minus 3. The answer I'm getting is minus 256 all over 27, which is equivalent to minus 9.5, almost 9.5 when I round it off to one decimal place. It's 9.5. Okay, then my second coordinate is 5 all over 3 is to negative 256 all over 27. It's becoming chaotic now. Let me try and erase all of this. 5 all over 3 is 2 minus 2, 256 all over 27, which is similar to, I'm just going to write this in decimals so that you can simply understand what are the exact numbers that we are talking about over here. This one is minus 9.5 approximately, and the 5 all over 3 is 1.7 approximately. Between those two numbers, which one has a higher y value or the lower y value? The 9.5 is below the 0 when you are drawing the Cartesian plane. The 9.5, the minus 9.5 is below the 0. The 0, meaning that this one will be our local minimum. Oh, sorry. I'm not pointing at which I should be pointing. This one will be our local minimum, and this one will be our local maximum. So we have the local minimum and the local maximum. We have our roots as well. Those are the only 3 things we need to be able to plot this graph. Then the next step from here is plotting your actual graph. Let us try and do a depiction of that. Minus 1, 3, minus 1. This is our x coordinate. This is our x-intercept. This is our y-intercept. And then the next thing is the 1.4, the 1.7, x being 1.7, say 2, let's say 1, can say 1, 2, okay. And then the 1.7, sorry, oh, I don't need that thing. I just need minus 9. So you're going to have x being minus 1, x being 3. And then you're going to have 5 for 1.7 minus 1 is to 0 again. And then you're going to have something of this nature. 1.7 is 9.4. Okay, I'm gonna have the other one as well. turning point. So it's gonna be it should be 1, 3. Okay, so it's gonna be this is the graph that comes out. So let us interpret this information. This is our local minimum, like we said. It's our local minimum. And this is our local maximum, like we said, where our rate of change is equal to 0 because the graph doesn't increase nor decrease at those 2 points. All right. Then our first root is also our turning point here. Our first root and our second root is also our turning point over here. Then our third root is here. That's how you draw the graph. I'll do a second segment of the video to show you the other two methods of finding the roots, namely the long division method and the synthetic division method. Thank you. Thank you for watching. Don't forget to like the video and subscribe.